When we looked at the motion created by the electric force in episode 38, we saw how the electric force attracts particles with opposite charges, but repels particles with similar charges. We can also explain this behavior in terms of the electric potential energy. Potential energy is manifested as two objects interacting through a force. In this case, we're interested in the electric potential energy between two charged particles. We can calculate electric potential energy using an equation that looks very similar to the equation for the electric force. We take the electric constant, multiply by each charge of the two particles, and then divide by the distance between the two particles. When the particles have charges with the same sign, their electric potential energy will be a positive value and will increase in strength if the particles come closer together. Just like in real-life experience, charged particles will tend to roll downhill, meaning they will always try to move from higher potential energy to lower potential energy. This is why similarly charged particles will move away from each other, while the oppositely charged particles will move toward each other. Here is our animation with an electron and a helium nucleus, where we've added three different graphing curves. One for the electric potential energy between the electron and the helium nucleus, and one for the total of the kinetic energy and the potential energy. The graph shows us that the electron tends to move closer to the helium nucleus since that will lower its potential energy. However, during this motion, the electron picks up more kinetic energy, which causes it to shoot past the helium nucleus, which raises its potential energy. This back and forth energy exchange continues, resulting in the orbital pattern that we saw last time. Notice also that the total energy remains constant throughout this exchange process. No new energy comes into or leaves the system. Now let's use these same graphs in our animation of the proton being repelled from the helium nucleus and the lithium ion. This time, the potential energy increases when the proton moves closer to the helium nucleus, which reduces its kinetic energy. In order to lower its potential energy, the proton must move away from the helium nucleus, and therefore its path deflects from its original direction. Then the potential energy begins to decrease until the process repeats when the proton gets too close to the lithium ion. Notice that the graphs of kinetic energy and potential energy mirror each other just like in the last animation, but this time the potential energy has a positive value. And again, the total energy remains constant throughout the motion. You have now learned how to study the electric potential energy using VPython. Follow the link in the description below to complete a set of activities to help you learn more about energy.